In this video, we're going to look at alkane halogenation, which is the reaction that you see at the top. Okay, here we're taking methane and treating it with a halogen. And out of this product, out of this reaction, we're going to get a halomethane and the hydrohalous acid. Okay, this reaction has to be catalyzed, or we say activated by either heat or ultraviolet light. And when we look at the mechanism, we'll see why that's required. X in this reaction, it has to be chlorine or bromine. Okay, it cannot be iodine because the reaction is endothermic. We'll look at that later when we look at how to calculate delta H for a reaction from bond energies, and we'll see that that actually is in fact the case. Okay, this reaction, I guess technically it does work with fluorine, but it's kind of a little hard to control. Fluorine is very exothermic in its reaction with alkanes. In fact, it's so exothermic it typically is explosive. It's very hard to control this reaction. I know a few fluorine chemists, and I don't think they all, a lot of them don't have 10 fingers, okay? It's a very dangerous reaction. It's hard to also get it to stop at one. You tend to replace every hydrogen in your molecule with a fluorine. Okay. Another interesting fact about this reaction before we consider its mechanism is the fact that reaction is catalytic in light or catalytic in photons. When we do the photochemical reaction, all we have to do is flash the light on for just a little instance at the beginning, and that's enough for the reaction to continue itself. Okay, the mechanism for this reaction is the first example of something called a free radical chain reaction. And a free radical chain reaction basically occurs in 3 stages. Initiation, propagation, and termination. Of these 3 stages, this is really the one that's most important. This is where the product forms. The initiation is very important because most organic compounds have all of their electrons paired. So this is the process by which you generate the first unpaired electrons. And termination is kind of just the opposite of that. That's where all the unpaired electrons get back together and form electron paired species. Okay, initiation in this particular reaction involves the treatment of the halogen with either heat or light. Okay, and what this does is it breaks the halogen bond. Okay, and we're going to use this symbol here, the half-headed arrow, to show the movement of a single electron. Okay, so from these 2 electrons right here, one of them is going to go to one X group and one of them is going to go to the other X group, and we will not have a bond between X and X anymore. Okay, so that's our initiation. Propagation. This is where most of the product forms. In this particular reaction, there are 2 steps in the propagation. We're taking the halogen radical here, and we're treating it, we're basically plucking the hydrogen right here off, and we're making a bond between X and H. This is one of the products, remember. And this generates a new product, and this is an organic free radical. And a free radical is just defined as a compound with an unpaired electron. This particular process is quite a common reaction in free radical chemistry. This is called a hydrogen atom abstraction. Okay? In the second step of the reaction, we're going to take the free radical and the halogen and an intact halogen molecule. Okay, this has an XX bond now. This is not a free radical halogen. This is actually the original starting material, either chlorine or bromine. We're going to abstract a halogen atom from a halogen molecule, and this is going to form the other product of the reaction, the alkyl halide, and this. This is now capable of going back into the reaction. Okay, this arrow here accounts for why the reaction is catalytic in photons. Okay, and if we look at this key product, most of the product forms here. Okay? In the final stage of the reaction are the termination steps of the reaction. And this is, if we figure out the termination steps of the reaction, all we do is we just take every radical, every unpaired electron species we generated throughout the reaction and just randomly combine them with other unpaired electron species. So there are three termination steps. The reverse of the initiation step is here. We can form the alkyl halide also by reacting a methyl radical and a halogen radical to get the alkyl halide. And to some extent we make a little bit of higher alkane by taking the alkyl radicals, in this case the methyl radicals, and combining them to make ethane in this case. Okay? Alright. Very little of the product forms in the termination step. This is because at any one time the concentration of radical species is very low. And when this radical species bumps into another molecule, the type of molecule it's most likely to bump into is not another radical, but one of these molecules that has all of its electrons paired. Okay, so the most likely collision is a radical with a molecule that's not a radical. So for this reason, we have to regard the propagation step as being the more important step than the termination step. Okay, we do not form very much of the product in the termination step. For lack of a better way to put it, the termination step is overrated as far as its importance in the reaction process goes. Okay, let's look at higher alkanes. And just one comment before we do that about this reaction. This reaction is a little bit hard to control. It's hard to get really good yields of products. Okay, and that's because the reaction is not restricted to monohalogenation. Okay, if you take methane and a large excess of chlorine, you can start to get multiple halogenation products. For example, not only do you make chloromethane, you can also make dichloromethane, trichloromethane, also known as chloroform or carbon tetrachloride. Even if you're very careful to add exactly 1 mole of chlorine, you'll see competition from these pathways. So you'll see not only chloromethane, but you'll also see unreacted methane and these overhalogenated products right here. Okay, so if we look at butane and we treat it with chlorine and light, and we're careful to isolate only the monohalogenated products, we start to see some degree of selectivity. We see that this product here, 2-chlorobutane, is the major product, and this is the minor product. Okay. If you look at the type of hydrogens we have 4 hydrogens at secondary carbon and 6 hydrogens at primary carbon. Okay, so what you see here is that this reaction's beating statistics a little bit, but not by all that much. Statistics would predict that we would get a 40 to 60 ratio. We do better than that. We get a 72 to 28 ratio. Okay, the bromine radical tends to be lower energy or more stable, and it's much more selective. So if we take butane and now treat it with bromine in light and isolate only the monobrominated products, what we see is actually a far more selective reaction favoring 2-bromobutane, which is also the major by a lot. Okay, it's a 49 to 1 ratio. Okay, so what we see from these two results is that the hydrogens at secondary carbon are more easily removed than those at primary carbon. Bromination is more selective than chlorination. This is because the bromine radical is more stable and thus more selective in its reactions. It's more selective for pulling off the more reactive hydrogens. Okay. In general, the hydrogens at the more substituted carbons are more easily abstracted, and the trend is that hydrogen at tertiary carbon is more reactive than secondary, more reactive than primary, more reactive than methyl. This is due to the greater stability of the free radical that you leave behind. Okay, and what we see here is that this is supported by the bond dissociation energies as well. Recognize that the starting material for each of these reactions here is exactly the same. Okay, so the energy of the starting material is constant. It takes 400 kilojoules per mole to remove the tertiary, even more to remove the secondary, and even more to remove the primary. Okay, and this has to do with free radical stability. Okay, free radical stability parallels carbocation stability for alkyl groups for the most part. And the structure is the same as well. So this is the structure of a free radical. Okay, so it's sp2 trigonal planar. Our unpaired electron exists in the empty p orbital. The reason for the stability has to do with hyperconjugation, but the hyperconjugation is not quite as strong as it is in carbocations. Okay, we never see a primary carbocation competing with a tertiary carbocation, but as you saw in the previous slide, the primary removal of the primary hydrogen, even though it's the minor pathway, is actually quite competitive with the major pathway in that case. So the difference isn't quite as large. I'll just draw an MO diagram here to illustrate this. So what we're looking at here is at the electron in the p orbital, and we have sigma and sigma star for the CH bond like we had before, and we have a weaker interaction than we would if it was a carbocation, because if we look at this MO diagram, the bond order equals 1/2. Recall that when we had a carbocation, there was no electron here, and thus there was no electron here, and the bond order was 1. Okay, so you don't get as much stabilization from hyperconjugation as you do in a carbocation, but you do get some, and this accounts for why a tertiary free radical is more stable than primary. Okay, bad planning on my part here. We're going to just predict the products of these reactions. These are brominations. The one on the left here, you can see that with this compound right here. Actually, this is the same compound here. We would predict that bromine and light would provide predominantly the compound where bromine is at a tertiary carbon. And if we go here, in this compound, the only hydrogen that it's a tertiary carbon is right here, and we would predict that you would get the compound where bromine is now at the ring junction. Okay, notice how we broke bonds and we correlated the relative stability of free radicals with bond dissociation energy. Okay, we're going to go a little bit further with this bond dissociation energy, and this is Hess's law, that the delta H of the overall reaction is independent of the reaction pathway. Okay? All right, so let me just give you an example of that. Let's imagine we have two reactions. Here's reactants. Here's products. Okay, in one mechanism, we're going to go like this. And the other mechanism will go like this. Now, the rate of these two reactions is expected to be very different because the rate is dependent on the activation energy. Oops, sorry, this is looking a little sloppy. And here's the activation energy there. But delta H here, delta G more accurately, is constant. Okay, it's pathway independent. So let's imagine that in this reaction, this is not the mechanism, but let's just imagine that we break all the bonds and put them back together. Okay, we know that the delta H for breaking the CH bond is we can figure that out from a bond dissociation energy table. We can break the bromine-bromine bond, and then we can put them back together, and that will be the negative bond dissociation energy for when we put them back together. Okay, so we can now make this equation out where delta H here would be the negative bond dissociation energy of the bonds that we make, and the positive bond dissociation energies of the bonds that we break. All right, so we can now have this important equation that delta H equals the sum of the bond dissociation energies for the bonds that we break minus the sum of the bond dissociation energies for the bonds that we form. And as long as we have a bond energy table, we can calculate delta H pretty effectively. All right, so the bond dissociation energy for methane, CH bond is 439. For bromine, it's 193. For bromine methyl, it's 292. And for HBr, it's 366. Recognize that these are the ones that we're forming, and these are the ones that we're breaking. Okay, so if we look at what we break, here's what we break. This is what we form. We work the math equation, and we get negative 26 kilojoules per mole as delta H for bromination of methane. Okay, here's a bond energy table. I don't expect you to memorize it. You can find bond energy table in any textbook. One thing I have to tell you about bond energy tables is that no two bond energy tables have exactly the same values. There's a variety of different sources for these, so you see small differences. And there's a lot of tables will use kilocalories instead of kilojoules. Let's look at some trends here. All right, so hydrogen bound to methyl is stronger than hydrogen bound to a primary. stronger than the secondary, stronger than a tertiary. We kind of already knew that. We see the same trend with the carbon-carbon bonds. The bonds between two methyls is stronger than the carbon-carbon bond between a methyl and an ethyl, and much stronger than a bond between the carbon and a tertiary butyl group. This one with the isopropyl looks to be an exception. I'm not sure why that's exactly the case. All right, we see that the bond strength to carbon increases as you go up in the periodic table. The carbon-fluorine bond is much stronger than carbon-chlorine, much stronger than carbon-bromine, much stronger than carbon-iodine. And that's a fairly general trend. Okay? All right, so let's finish this out with doing a bond energy calculation of your own. You should do this by yourself, pause it, and then come back and look at how I do it. Restart the video after you've done the calculation. All right, so what's delta H for iodine participating in this reaction? All right, so what do we break? We break carbon-hydrogen at methyl, and we break iodine-iodine. Okay? Break and break. What do we form? We form carbon-iodine. And we form hydrogen-iodine. Okay, so let's use those values. Let's plug those into the equation. Broken altogether is 590. Formed altogether is 389. Delta H is plus 201 kilojoules per mole. This reaction is not feasible. By the way, if you're ever designing a new reaction, sorry, I forgot to turn the email off. Okay, if you're ever designing a new reaction, you should always calculate its bond energy, because the probability that it will be successful is much higher if it's an exothermic reaction than it's an endothermic reaction. If it's extremely endothermic, the chances that it will work or actually go down quite a lot. Okay. All right, so this is the last slide in this video. Let's just predict the products of these reactions. What we're going to do is look for the hydrogen at the most substituted carbon and just substitute that with the appropriate halogen. And a valuable clue here is that benzene rings are not reaction sites in these equations. Okay, we're going to see that benzene rings have a special reactivity of their own much later in the class. Okay, so we're going to ignore those hydrogens on the benzene ring. Hydrogens here would be at secondary, 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 tertiary, secondary, secondary, and secondary. Thus, we are going to take the hydrogen that's here and substitute it. The product of this coupling is of this halogenation should be the compound that you see right there. Okay. In this next one, again, the benzene ring is not a reactive site. We're going to look at the hydrogens in the molecule, the remaining hydrogens in the molecule, and we see these hydrogens are at primary, primary, and primary carbon. There is no really good place to substitute. Okay? And this is our product. A common wrong answer that I'll get on this equation, somebody could be really desperate to give us a tertiary halide. And this, of course, has to be the wrong answer. This is because we had to break carbon-carbon bond. We can't do that. Okay? All right, this last one, sorry about the placement of the methyls into my writing there, but has hydrogens at primary, 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 secondary, 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 and secondary. If you look at the symmetry of this molecule, you see these are actually the same. And these are also the same. Okay, you have two different secondary sites here. So this reaction is predicted to be not all that selective. You should get this compound than this compound. You could probably say that maybe you get a little more of this because these methyls here are kind of large. In the previous chapter, we made a big deal about steric effects, right? So these hydrogens here would be a little bit harder to get to, so we probably expect this compound here to be the major product. Okay, this is going to end the videos in chapter 4. We're going to revisit alkyl halides and their reactivity in chapter 8, and we're going to revisit alcohols and their reactivity in chapter 14. Okay, but it's important to know how to make them, and this reactions that you saw in this chapter are very important methods for doing that.